Hello everyone. My name is Wataru Fuji from University of Tsukuba, Japan. The title of my presentation is a Pseudo Optical-Axis-Matching Projector-Camera System by using Intermediate Viewpoint Image Generation. Let me explain the background of our research. Have you ever heard of projection mapping? It is a technology to project 2D images onto a 3D object by a projector. This is a demonstration of projection mapping that I actually performed. Light is projected onto a mannequin wearing a blue uniform, changing the uniform's color to red, green, or blue. In this way, projection mapping can change the appearance of an object. For example, colors, patterns, textures, and so on. In some applications, the object's position or shape is not known in advance. To respond to such real-world situations, it is necessary to build a projector camera system that combined a projector and a camera. The camera takes a picture of the scene, including the projection target, and sends the information to a computer. The computer recognizes the scene and generates the image. Then, the generated image is projected from the projector. For the system to operate correctly, the geometric relationship between the projector and camera must be known accurately. However, it takes time and effort. So, this is a problem of projection mapping. To address this problem, a method to match the optical axis of the projector and the camera is being considered. As shown in this figure, if the optical axis is the projector and the camera are matching, the pixel correspondence between the projected image and the captured image can be uniquely determined. No projector camera calibration required in the projection scene and independent of the position of the projection target. However, as shown in this figure, it is difficult to place the projector and camera in the exact same position. In the previous research, optical axis matching was performed using a beam splitter. Light from the projector passes through the beam splitter to reach the object. The light from the object is reflected by a beam splitter and reaches the camera. The optical axis of the projector and camera are matching between the beam splitter and the object. The advantage of this method is that the projector and camera are located at different places. The disadvantage is that there is a trade-off between the reflect and transmit of the projector. Of the beam splitter. It is difficult to ensure both the luminance of the projected image and the amount of light incident on the camera. Our research proposed a method of pseudo-aligning the optical axis of projector and camera by using intermediate viewpoint image generation. This is an overview diagram of the proposed method. There are 3 steps. We set up 2 cameras on both sides of the projector. Step 1. Each camera captures the scene of the projection target, the right viewpoint image and the left viewpoint image. Step 2. Disparity of the two captured images is estimated using stereo matching. Step 3. Based on this disparity information and the left viewpoint image, we generate the intermediate viewpoint image. This image means the image observed from the optical center of the projector. In the part of step 3, the process of determining the pixel correspondence between the input and output images is performed. I will explain about this part in detail. Okay, this task can be divided into 3 processes. The purple and orange rectangles are shown on the right side on this slide. The purple rectangle represents the input image captured by camera L, and the orange rectangle represents the output image observed from a projector optical center. Process 1, we choose the target pixel and the input image and obtain its 2D coordinates. The target pixel is represented by a red dot point. Process 2, the target pixel is transformed into a point in 3D space. We use the estimated disparity information and the internal parameters of camera L. The 3D point obtained is represented by a red star. Process 3, the 3D coordinates are converted to 2D coordinates in the output image using the internal parameters of projector. The resulting 2D coordinates are also marked with a red dot point. By these 3 processes, the pixel correspondence between the input image and the output image can be found. The pixel values, that mean color tones, obtained in the input image are applied to the corresponding pixels in the output image. These processes are applied to all pixels in the input image. Then we can generate the output image. This is a projector camera device that we constructed for the experiment. 2 cameras are set up on both sides of the projector. When facing the projection direction from the position of the back of projector, camera R is located on the right side of the projector and camera L is located on the left side. These 2 cameras were positioned same distance and same height from the optical center of the projector. To prevent the projector and camera from being misaligned after camera calibration, they are fixed with bolt and nut using aluminum plates. Here is how the filming experiment was conducted. The program device was arranged as shown in the photo, and the scene was prepared with a mannequin wearing a blue uniform as a projection target. These are images captured by the 2 cameras, camera L and camera R. Please look at the mannequin player wearing a blue uniform. In the left viewpoint image, he is positioned closer to the light. In the light viewpoint image, he is positioned closer to the left. This is the disparity estimation step. The image in the center is a generated disparity map. We use a model called HIT-net to estimate disparity. Dark purple areas are small disparity and far from the camera. Light yellow areas are large disparity and near the camera. The result of generating the intermediate viewpoint image using this disparity image is shown here. In the intermediate viewpoint image, the mannequin is located at the center. Areas that were shaded by objects from the left viewpoint image are represented as black missing areas, as they cannot reflect pixel values in the output image. To complement the missing areas, two processes was applied. As the first process, a median filter with a kernel size of 3 pixels multiply 3 pixels was applied. As a second process, an inpainting process using Taylor's algorithm was applied. This is a magnified view of a portion of the image. The median filter removes the fine noise, and the inpainting process fills in the black areas. This is summary of my presentation. Thank you very much for your attention.